So in 18, you're doing the integral. The integrand function itself doesn't look too hard, 4 minus 3y. But the region is bounded in kind of a strange way by y equals 0, y equals x over e, and y equals ln of x. You should feel comfortable writing it in an abstract form like that with a dA. Okay, it's just sort of an abstract form. Few different things emphasizes the double integral, two integral signs for one thing. The dA and the r down there emphasize it's a double integral. The region, y equals 0 is the x-axis. That's y equals 0. Y equals x over e is aligned with the slope of 1 over e. And y equals ln of x. And if you use your calculator, these graphs do touch at one point there when x equals e, right? When x is e, e over e is 1, and also ln of e is 1. This is y equals ln of x. So the region in question is this kind of triangular shape, except one side is not a straight line, it's a curve. Problem says to do the integral, 11 through 18, sketch the region. So we sketch out the region, set up both integrals, both iterated integrals, and evaluate one of them. When you see these kind of directions, realize it's very possible that one of the integrals may be a lot easier to do than the other. In fact, it's possible for one of the integrals to be easy and the other one to be impossible. And that even happens, I believe, in number 22 here. Basically, doing it the way it's shown here, number 22 is impossible. But when you switch around the order of the integrals, switch around the dy and the dx, it becomes possible. In fact, it becomes easy. You can even do it just thinking about it. The answer ends up being 0 for 22. But let's do 18 to finish here. If we do it sort of the more typical way, thinking about this region as being between the graphs of two functions of x, it's a little trickier. We either have to treat the bottom of the region as a piecewise function, or break up the region into two pieces and add two integrals. That would be doing it with respect to the order dy dx. When you think about it as being the region between the graphs of two functions of x, the ordering is the opposite of what you might guess. It's dy dx. I always have to rethink about that myself, but I've been thinking about it recently, and so now I'm remembering it. So to set it up with regard to the order dy dx, let's do it as the sum of two integrals. For the first integral, it's over the leftmost piece. X goes from 0 to 1. We're doing dy dx. That's going to be the outer integral limits, 0 to 1. The inner integral is going to be the range of values that y goes between as functions of x. This one down there is a constant function of x, 0, so that's nice. That one up there is not a constant. It's x over e. 4 minus 3y, again, dy dx. The most ordinary way to think about this, you'll be doing dy dx, not dx dy. That makes sense when you think about it as an iterated integral. But the limits of integration depend on x. When you do this integral, you'll treat x as a constant if there were an x in here. Integrate with respect to y, then let y go between two functions of x. When you plug in those functions of x, the result will depend on x. And you integrate that with respect to x. For the second integral, x goes from 1 to e. And the lower limit of integration becomes the lower function there, ln of x. And the upper limit of integration is still x over e. It's still the same integrand function. It's still dy dx. Actually doing these inner integrals, it's not hard because you're integrating linear functions of y. Finding the antiderivative is pretty easy. Plugging in limits of integration, though, could result in an integral that's trickier. For one thing, you'll have an ln of x involved. You might have to use integration by parts to help you finish the problem if you do the calculation this way. But maybe it's going to be better to actually do the calculation with the other way. Think of this region as between the graphs of two functions of y. This is y equals x over e. That's equivalent to x equaling e times y. That's y equals ln of x. That's equivalent to x equaling e to the y. It's possible it could be easier. It could also be harder. One definite benefit is it's only going to be one integral instead of two. Now it's going to be with respect to the order dx dy. The outer integrals with respect to y. Y goes between 0 and 1. So it's going to be just one double integral where the outer one goes from 0 to 1. And the inner integral goes from, you go not from up to down, or from down to up, you go from left to right. Y, or x is what's varying here between two functions of y. The smaller function is on the left, the bigger function is on the right. So the lower limits of integrations, e times y, and the upper limit is e to the y. Let's go ahead and start doing this one by hand and see how it goes. Integrate with respect to x, so I treat the y as a constant, so I effectively just get that constant times x. X is what goes from e to the y, or e times y, excuse me, e times y to e to the y. Tricky, be careful there. You get something sort of complicated looking. 4 minus e 3y times e to the y minus 4 minus 3y times e times y. Integrating that part's not going to be too hard because it's a polynomial. It's e times y, not e to the y. This one's going to be a bit harder because you're going to have to use parts. You could expand it out and just focus on that part as being the hard part. Maybe you want to do it as a separate calculation. Just an antiderivative y e to the y. Just in case it's not something you have memorized. Use parts. In some books, you start with a u and a dv. You'd want u to be y and dv to be e to the y dy. In other books, like the calc book we use, they call this v prime. Is e to the y. Find du or u prime. Based on u being this, the derivative of y with respect to y is 1. So du is dy, or if you think of it as u prime, the derivative is 1. Integrate this to find v, it's just e to the y. The formula for integration by parts looks like this, or like this. Depending on which book you use. Hopefully you've done enough of these in your past to not be too confused by the fact that I'm using a couple different forms. You get y e to the y minus the integral of the product of those would be e to the y dy. Y e to the y minus e to the y plus c in general. But ultimately you're doing a definite integral, so you can take the c to be 0 when you use that up there. What is the final answer? I'm going to let you finish that. You may already be finished, but let's just confirm the final answer. And let's also confirm that both integrals give you the same final answer. So I'll do the first one as well as the sum of two integrals. Integral from 0 to 1. Tab over, do another integral from 0 to x over e. Use a capital E, in case you've forgotten in Mathematica. Don't forget the second integral for this first one. Oops. I don't think I hit that button again. ln of x in Mathematica is actually log. More Mathematica stuff here. 3e minus 7. Did you get that for the answer? The other one should be the same final answer. Just one integral. 0 to 1. E times y to e to the y. Same function, but the opposite order for dy and dx. It becomes dx dy now. Same answer. For the sake of starting concepts about center of mass and center of mass, and maybe even relating it to probability, let's also think about this in those ideas, with those ideas. If this function 4 minus 3y represented the density function for a thin sheet of metal shaped like this. Say that again. If this function 4 minus 3y represented the density function in mass per unit area, pretending this region here is like a thin plate of metal, really, really thin, effectively so thin you effectively treat it like a two-dimensional object. And you think of the density as giving you approximations to the density in grams, say, per square centimeter. Then doing this double integral like this gives you the total mass. That's a general principle to know. So if that were the case, then this number 3e minus 7, which is about 1.15, would represent the total mass of this sheet of metal. Again, if the units for the density function were grams per square centimeter, then the units for the answer here would be in grams. Can you do that in this situation? Does this make sense? It is a possibility here in this case because this function, 4 minus 3y, is positive over this region. If I plot this, x going from 0 to e, y going from 0 to 1, and use the region function to specify the domain to be the thin sheet of metal, which I can specify with inequalities like the inequalities for the integrals. It'd be simplest to use the one that only involved one integral. Y goes from 0 to 1, and x goes from e times y to e to the y. I could do that like this. I could go y goes from 0 to 1, and use a double ampersand for and. X goes from e times y to e to the y. That's the graph of this function over that region. And it's always positive. Density functions can't ever be negative because you can't have a negative density for some thin sheet of metal. And once again, this integral, the integral of this function, if it is the density, does give you the total mass. This can be reasoned out by thinking about cutting up this thin plate, this thin sheet, into tiny little pieces of area dA, say, in square centimeters. Say that's in square centimeters. That's a tiny little area element. And if you multiply by the function, where the function is giving you grams per square centimeter, and you pretend this is a product, the square centimeters would cancel, giving you something in grams. And integrating is supposed to be analogous to adding. adding up these tiny masses to get the total mass. That's an intuitive approach. It's not rigorous. It's an intuitive approach to why doing the double integral of such a density gives you the total mass. Now, you might be thinking too practically about things and be wondering, how would you manufacture some thin sheet of metal that's got such a density function? Well, if you think such thoughts, well, good for you, but you're being a bit too practical for us, okay? Maybe it's possible to manufacture such a thing, though if it is, I don't know how. But we're thinking theoretically here, and it does have some value, especially I'm imagining in like a mechanics class, because it ultimately can help you find the centers of mass of things. Center of mass in this kind of situation would have coordinates that are sometimes called X bar and Y bar. Center of mass. And to figure out those center of mass coordinates, this is still relevant for integrals, you have to compute ratios where the bottom of the ratio is the mass in each case. M represents the mass, which again is the double integral of the density function over R. And the numerators are also computed by doing integrals. And those integrals are called moments. Kind of like moments of inertia. And yes, you can relate this to rotational kinds of things and torques and that kind of thing, though I don't want to get into details. The one for X bar is actually labeled M sub Y, and the one for Y bar is actually labeled M sub X, so it's a bit confusing like that. There's a reason for it. M sub Y turns out to be a double integral over the region of X times the density function. Y, use a subscript of Y, no pun intended until I just said it. The reason is because by multiplying by X, you're measuring the distance from the Y-axis, the sine distance, that's Y. We're using M sub Y as it's a moment about the Y-axis. Think about a little picture here. Well, we can redraw the region. When you're thinking about multiplying X times f of xy, you are effectively in the X here, you're measuring horizontal distances to the Y-axis. A moment about the Y-axis. That's why using a subscript of Y is what you do. And the mx is the double integral of Y times f of xy, because you're measuring a distance from the x-axis.